John is still part of the center, but he's now working for NVIDIA, so he joined the dark side. So thank you, John, and we are looking forward to your talk.
Very good. Yeah, I joined the green side. That's what I'd say.
Yeah, I
So,
understand.
so today, what my contribution to the workshop is maybe to tell people about some of the things that make VMD unique or different compared to other programs. There are many visualization tools available, and they each have their strengths and their areas of greatest applicability. And I think one of the things that is, the history of VMD makes it somewhat different than the other tools. So one of the things that's worth noting is that VMD was designed for visualization of molecular dynamics simulations from the very beginning. And so VMD has always dealt with time varying data, so time series, trajectory data of various kinds. And in the early days, it was written to just work with proteins and things like this. And over time, we have made VMD more flexible, taught it how to understand a greater diversity of structures, different types of different modalities of molecular simulation. So that includes not only all atom structures, which is what VMD started with, but going toward information coming from coarse grain modeling, a variety of different coarse grain approaches, going to lattice cell simulations. I'll share a couple of those, quantum chemistry simulations, and then lots of, another area that VMD grew a lot over the years was incorporating various types of experimental imaging information. So cryo-EM density maps, tomograms, a variety of volumetric data, whether those are electrostatic fields, density maps showing spatial occupancy, all kinds of different things. And so those, the access to those data are what make it unique in some sense. A lot of other tools focus on a particular subset. VMD was more of a generalist. Another thing that made VMD somewhat unique is it was built from the very beginning with embedded scripting languages. So some of that is now today a more commonplace consideration, I would say, or people have realized that that choice was very powerful. But in the era when VMD was originally developed, that was unusual, and almost none of the other tools had taken that path. Another thing that's sort of different from VMD and others is the use of a common atom selection language, which is used not only for visualization and creating the images, but also in doing your analyses. So you use the same language, and the use of a language rather than pointing and clicking at everything. That was something that made VMD very well suited toward working with very large structures. So as you can imagine, if you imagine doing a Google search, you could do 1,000 clicks to find something, or you can just ask Google to find it for you. That is sort of, there's an analogy there between how you find things on the internet at large with a large set of data or a database query, and what we do in VMD when people select atoms or structures that meet some criteria. It makes it easier to extend the power of that program to work on very large structures. So things like viruses, these cell scale models, et cetera. So you can use that same feature both at the very small scale, working on protein ligand docking and things like that. You can use that over time to find things in a long time series. And you can use that also. I see somebody's got a chat there. There we go. And you can use that over large structures. So I'll go to the next slide here, if it cooperates. There we go. So, VMD doesn't work in isolation. It works with simulation tools. So on the last slide, I had that diagram that showed how VMD connects to tools like NAMD, Amber, GROMACS, and many others. The VMD in concert with structure preparation tools and the various simulation tools that it connects to, it provides the scientist with sort of a computational microscope. So we don't just want to see those structures, although that's very important. We want to be able to measure their physical properties. We want to be able to make changes to those structures, to evaluate various things. And we want to be able to do that over all of the biologically relevant spatial and temporal scales. And, one of the things that has driven that over the last 30 years has been the availability of experimental structure information. So you've seen this slide, I think, in Diego's talk on Monday. What I would say is interesting for VMD, the reason VMD is able to work on structures that cover this entire range of size and timescale is because over the period that, I and others worked on the program, we invested a lot of energy into making it use efficient data structures. So VMD is able to work with very, very large structures because it is very memory efficient. We paid a lot of attention to how it stores structure information, how that information is accessed, and how it's read or written to and from files. And so that's the reason we're able to get to structures that are in the billion atom size range. Some of the things that are kind of interesting about VMD, in conjunction with trajectories. Oh, my movie isn't going to play, so I guess you don't get to see the movie today. Too bad. You can also do things like temporal. You can do analyses where you compute occupancy and things like this in a spatial region, and that can be time averaged over the course of a trajectory, and you can use that to make 3D maps. And now one could do these things in Python or in MATLAB or other tools, but being able to do it in a tool that understands what a molecule actually is very powerful, and it makes it easier for you to use that information in other analyses that you want to do. So you not only can you see those things and visualize them, but you can use the outputs of that kind of analysis to do further queries. Some things that make VMD unique versus other tools are also that we adapted VMD to run on parallel computers. So this is not the conventional version of VMD that you just download off the website. When you build tools to run on supercomputers, you probably heard about compiling things on supercomputers, like if you run at Texas Advanced Supercomputer Center or at NCSA or one of the other NSF-funded supercomputer centers, for example, you often have to compile the simulation codes that you use on those machines so that they can use MPI or whatever message passing system they're built on. VMD is the same way. We have a build flag for VMD that allows it to be compiled for MPI. And then you can run VMD on a supercomputer and use large node counts to do things like process large trajectories. You can do any analysis that you would do on one frame, you can do on an entire trajectory using a large number of nodes. So as an example, this is more than a decade ago here, we had a particular kind of analysis doing cross correlation between atomic structures being simulated in cryo-EM density maps for doing molecular dynamics flexible fitting. This is a structure determination method, or ways of taking crystal structures that have various deformations and turning them into a structure that is docked with cryo-EM, which is thought to be more representative of the in vivo state of those structures. So that, is, it turns out, is very computationally demanding calculation. So doing that cross correlation analysis, one of the things we did is we first accelerated that analysis by adding a new CUDA kernel in VMD that knows how to do that on the GPUs. And then we used the MPI version of VMD to take that type of analysis and run it not just on one node, but to do it on a very large node count. So you can see here, doing this for rabbit hemorrhagic disease virus, on a trajectory with 10,000 frames, calculating those cross correlations on different components of the virus, and then doing this brute force calculation. This would take 14 days if it were on a single node with a GPU accelerated node. This is 10 years ago, so GPUs are way faster now, but the point is the scalability, right? So that would be just as true now as it is 10 years ago. If we run that on 128 nodes, it cuts that runtime down to 3.2 hours. So we get a speed up of 105 for 128 nodes. That's pretty good. And then if we go to 2000 nodes, we can cut that all the way down to about 19 minutes. So that's pretty amazing. I'm not aware of any of the other visualization codes that exist in this domain that can do anything like this. So this is a unique um, capability of VMD versus the others. I would say, you know, this example, while it happened to be orientated toward cryo-EM fitting and things like this, there are many things where we can use this functionality of VMD. That you can use this for rendering movies of large trajectories. For example, we made many movies, you know, of virus simulations, things like this that are computationally demanding and or very high resolution movies, things like that. Those can all be sped up in the same way. You can use the same thing to do analyses, not just of frames within a trajectory, but that you could do that for multiple trajectories at the same time. So if you have replica simulations or other things you want to analyze, those are something that would be possible using the same technique. So, and this is all done in a way that is exposed through VMD scripting. So if you can write a script to run on one node, you can do it on many nodes. VMD has some features for doing things like density map segmentation. You know, one of the problems you have when you want to analyze or visualize density maps, they are just a three-dimensional grid of scalar values, right? And so a computer by itself doesn't really understand anything about what those values mean. So you have to infer meaning from those values using very sophisticated algorithms. And what segmentation algorithms do is they find connected regions of space that have similar densities. And there's a famous algorithm called the watershed algorithm. This algorithm and others like it will basically label those connected regions of density with an index, right? And once those things have an index, then you have a way of referring to them in scripts, you know, interactively in a user interface and so on. Once you can refer to those things, now you can refer to particular subunits of a structure in that density map. And you can use that then to do more targeted analysis, like how does that part of this density map fit with the crystal structure? Are they well aligned? Is there disagreement? Can I identify a particular region of space where those are poorly docked or poorly aligned and so on? So those are all things we can do using density map segmentation. At a large scale, these things are used to prepare simulations for cell scale simulations. For example, the lattice microbe software, you can see in the bottom right corner, there's a lattice representation of a 3D tomogram. So the original tomogram is particular resolution. Those get those densities are then first segmented and then they're classified by what type of particle species they are. And then that becomes input to doing a lattice cell simulation, and the rest is you know, straightforward. Some of the things that you can do with the built-in features in VMD, these are visualizations that one of my colleagues, Tyler Ernest, made several years ago. They are lattice cell simulations. All of the visualizations you're seeing here are produced in VMD and rendered entirely in VMD. This is all done just using the scripting and the built-in VMD plugins. He made a very sophisticated set of transitions and zooms. You can see he's peeling away different surfaces, applying different representations, showing different detail and so on, and then showing the dynamics of this cell simulation, all using the built-in features of VMD. So you can do this too. It need not necessarily be a cell simulation, but those mechanisms exist within the software and they're available for your use for whatever your purposes are. So just to give you an example of the efficient representation and storage, you know, the efforts that were put in to VMD to make it performant for doing large trajectory visualization and analysis are just as applicable and maybe even more important for people doing coarse grain simulations of large structures like minimal cells. And so just as an example, there's a laboratory at University of Illinois, Zan Luthi Schulten's lab has developed this lattice cell simulation software. They are collaborating with various other labs all over the world to simulate these cell size systems with coarse grain force fields. And one of the examples of the benefits of the efforts we put into VMD show up in just doing run-of-the-mill cell simulations here with a system with 100 million Martini beads without any solvent even. Some of the conventional software packages out there that aren't quite as tuned as VMD use, I guess I'd say legacy, these are legacy file formats. There are better ones out there, but the devil's in the details. And one of the things we can do is use more modern software approaches that give with VMD tremendous performance benefits. So just as an example, one of the collaborators that Zan's lab had was loading large structures into VMD, and were asking us how to make that faster. You can use a particular file format that's built into VMD and NAMD called the JS format, and that is a trajectory format like many others, but it's been optimized for SSDs, so it performs much better on state-of-the-art hardware than some of the legacy file formats do. And in some cases it's more compact, but mostly it is much higher performance. So it's not really a compressed file format or anything like that yet, but it does perform much higher speed. And so just as an example, you can take something that would have taken about 190 seconds to load for a 4.5 gigabyte file. And due to a combination of reduced file size and more efficient storage and structure, the same thing can be loaded in 49 seconds just in the JS format. And then going a little further with some optimizations in VMD and making better use of atom selections, this can be made another 6 times or a total of 6 times faster than the original, just by being smart about how we use these structured data. So another thing that's interesting is VMD has plugin mechanisms, and that's all of what I've described here were implemented with VMD file reader plugins. There are ways to do plugins not only for structure data. So structure is the particles and the bond topology information about their atom types and so on, or their particle species, but also time series data, trajectories, and density maps or volumetric information, density maps, tomograms, electrostatic fields. And so if you have written your own software, you can write your own plugin and connect that to VMD. You can, if you are working with a particular simulation code and there's not already a reader for that data, it's very easy to write such plugins. If you're familiar with C or C++, it's pretty straightforward to do this. And one of the things we're interested in doing is taking advantage of some of the state-of-the-art technology that's coming out of companies like NVIDIA, but also the visual effects industry and other places where new file formats have been designed for things like sparse volumetric data. So there's a format called VDB, which is very widely used in industry in visual effects originally, and that is now becoming a very widely used format. And there are now some descendants that are specifically tuned for use on GPUs, so they can be used not only for visualization, but also for analytical purposes. And some new work now using neural networks for compression of these volumetric data. And this can make these volumes between 2 and 100 times smaller than a conventional 3D grid of scalar values represented in floating point. So if you can imagine, you have a sparse volume, even this cell model I'm showing here, which is densely packed in its interior, if you were to have cryo-EM data for this, it would be sparse because the corners of the volume would be empty. You wouldn't show the solvent. And so those kinds of things are a tremendous opportunity to make the software more performant. Another area where VMD has been a leader, I would say, over the last 20 years has been in the use of advanced visualization technologies. So beginning with things that are more fundamental, like rendering, VMD, in part maybe because of a lot of my expertise, VMD was one of the first molecular visualization tools to incorporate ray tracing in a significant way. So this goes back actually something like 22 or 3 years. VMD began incorporating ray tracers directly in the program. They're actually compiled into the software, and as a result, VMD is designed to work well for both conventional rasterization, which is what you used to see in video games and so on, and the ray tracing methods that are now state of the art. Ray tracing, I'll get into in a little bit, allows us to do visualizations that are more informative. So it isn't just that they look nice, but they're easier to interpret. And I'll talk a little bit about that as we go along. Some of the things that are nice about ray tracing are that we can parallelize that on state-of-the-art GPUs and similar hardware. Ray tracing can allow us to do things like make 360-degree panoramic videos like we would use for YouTube to use with VR headsets. So if you want to make a trajectory movie showing your simulation and then share it in a VR headset, you can actually render these in VMD, upload them to YouTube as a 360 VR video, and then you can play this on your favorite Meta Quest or whatever VR headset you like to use. And a cool thing now that these VR headsets are self-contained, you can actually take these to a poster session and give a demo, a live demo at a poster session, have your VR headset with you and show other people your simulation results in 3D. And so some of the things that are beneficial, I used to get people asking me questions, why did we put in the energy to put these advanced rendering engines in VMD itself? People had asked me, why don't we do this in, say, Blender? I mean, you can, and VMD supports interoperability with tools like Blender and many others, but there are some advantages to doing the rendering inside of VMD itself. And some of the key things that we get out of doing that are much, much higher performance because we aren't writing a molecular scene to a disk, and we get to use a internal representation, or we get to exploit VMD's own understanding of the molecular structure to make the visualizations. And one of the key things we care about actually in molecular visualization is rendering curved surfaces. We draw an awful lot of geometry that is curved, and so we care about those things looking nice and being actually curved, and not only on geometry like the atoms or the bonds, spheres and cylinders, but also we want smooth interpolated colors on density maps and isosurfaces and things like that. These are all things that we can do when we maintain all the information that VMD has. And so by building the renders into VMD, we get to keep all that information. Another thing that's kind of interesting, ray tracing, because of the way the algorithms work, it is actually a lot better at handling curved geometry, spheres, cylinders, cones, and so on. And that is because the way ray tracing is done, you don't draw millions of triangles, you actually draw curved surfaces by solving ray surface intersections. And that leads us to, something that is more directly, based on the atomic structure or the coarse grained structures to begin with. So just as an example, why do you care about ray tracing? For, if you're a scientist and you don't really need to understand how it works, you might say, well, why does ray tracing matter? Well, one of the reasons is ray tracing methods allow us to do lighting and shading calculations that in a way that's fully automatic, that is much easier to interpret for an end user. So if I look at two examples, on the left, we're using very simple lighting. This is the lighting that is used in video games going back, multiple decades until very recently. And more recently, there are a number of ways of accomplishing this, but on the right, we have what we call ambient occlusion lighting. If you've ever talked to somebody who's a photographer, you will have probably heard the advice that it's better to take photos outside on an overcast day rather than when the sun is straight overhead and beaming down on you. And the reason for that is when you have an overcast day and you have clouds, it diffuses the light in all directions. And so you get sort of an omnidirectional lighting pattern. And the result of that is you get very fine gradations in shadowing. And those fine gradations in shadowing allow you to see surface details. So for example, here we have a virus capsid. This is a satellite tobacco mosaic virus. On the left, you see, these are both the same structure, by the way. So on the left, we have cut open the virus capsid, but it looks like a flat plate of spaghetti. You can't really see any detail at all. On the right, all we have done is used ambient occlusion lighting, which gives us this overcast kind of omnidirectional lighting. It takes a large number of samples per ray. So it says, in this case, we've got 144 randomly oriented light directions. And by doing it this way, we get these fine gradations in shadow tone, and you can, without doing anything as a user. So I used, the reason these are colored white, or I gave them a flat gray color like this, is so that the only thing you're getting out of it is the shadows. And all it takes to get that 3D depth perception is to turn on this ambient occlusion lighting. And so you as a scientist, you don't have to learn how to become an expert in lighting. You can just literally just turn this on, and no matter how you rotate the structure, you will get high quality lighting from any angle. So that's another thing. If you're doing an animation of a trajectory, a long simulation, and something is twisting around and moving a lot, this kind of lighting gives you a good result without you having to do anything manually to fix it. So that's the value of the technique. So that lets us do things like show things like these pockets, pores, and cavities. If you look at this is the same virus capsid. Now we've applied radial coloring. So we're just coloring the capsid by radial distance from the center of mass. And so you can see that helps you see the outermost parts of the surface more clearly. When we combine the color with the shading, in the shadows, then we can see this 3D structure that much more clearly. And another thing I would point out, if you look on the left, when you have a more sparse structure, you have something that is very stringy, as proteins are. When they're spread out front to back in space, or you're zoomed in significantly, like in this case, you can use depth cueing to accentuate that 3D perception. So you're basically shading things, adding a fog effect to what you're seeing. And so the things that are farther away are going to blend into the background. If you make the background black, they blend into black. If you make the background white, it blends into white. So VMD's depth cueing just uses whatever the current background color is to do that depth cueing. One of the other benefits of ray tracing methods is they can simulate various optical effects like transparency much better. So if you're doing surface renderings, for example, in the top left, we have light harvesting structures that you can see little chlorophyll rings, the little green circular structures there, and carotenoids are shown in orange. And we've got the surfaces there for context. So the surface is there just to show you the overall structure and the placement of those chlorophyll rings within that structure. This is a very common need when you make your own molecular visualizations. You're going to want to show a key site where something that is biophysically interesting is taking place, but you want the context of what, that whole system shown in some way. So VMD has a bunch of sophisticated ways of drawing transparent surfaces. The one here that is shown is somewhat basic, but the advanced rendering methods make those work very well. In the bottom left, I made a very exaggerated scene here. This is one that one of our friends, Josh Vermas, made for me originally. And this is showing off what is called depth of field. So that's where you, much like with a camera, you can choose what is in focus and what is out of focus. So there's a camera has a plane of best focus front to back. That's another way of showing context, but drawing the user's attention or the viewer's attention to a particular part of the structure. And so I'll show some more examples of that as we go on later. But depth of field, if you combine the use of depth of field, depth queuing, and all these things together, you can start to make images that communicate very effectively. One of the cool things about the ray tracing methods in VMD is that they perform very well even for huge structures. So I think this, if I recall correctly, is about 15 million atoms for the lipid membrane and the chlorophyll rings and antenna complexes in the chromatophore. That's a light harvesting structure. And this kind of scene on a modern GPU, you can rotate this around in real time with ambient occlusion lighting, and it's no trouble at all, not even a challenge with a ray tracer. Doing that with rasterization with regular OpenGL or Vulkan is very difficult. So this is a case where there's a little bit of a threshold, like the main OpenGL display does very well for, you know, run-of-the-mill 100,000 atom structures, but as you get into the many millions or hundreds of millions, the ray tracing renderers start to become more interesting. And in the context of the next version of VMD, something that exists in a prototype form is a real-time ray tracing version of VMD where the entire user interface in the main VMD viewport is done with ray tracing rather than with rasterization. And so that all these things that I'm describing, the goal then is that this will become all you ever see in VMD. So it isn't there in the versions that you see on the download on the website right now, but we have a you know, sort of a prototype version implemented where the ray tracer runs all the time. And so other things we can do with materials, I think Diego is going to give you guys a talk about how to make sophisticated images and movies in VMD using some of the built-in features. I'm just going to make you aware of some of the things that exist. Aside from the sophisticated rendering, we also have shaded, you know, sort of programmable shaders built into VMD that can do things like outline edges of structure. So I just took, in this case, a couple of sample structures and I, you know, gave a particular camera view where it would be hard to see the depth. So in this case, I played against, you know, the things I was pointing out before, just to show the value of edge outlining. If you have a scene that's composed only of spheres, for example, sometimes it's hard to tell what's in front and what's in back, or if for whatever reason you can't use depth queuing or ambient occlusion lighting in the way that I was describing, you can use edge outlining as another way to show where different, sort of like a topographic map or contour lines, they help the viewer understand the depth relationships between the things in the scene. And I would just say that in this one, you can see there's tremendous depth of field. So on the right-hand edge, it's being blurred out as things are farther away. The edge outlining can be made strong enough that it's visible even when there's a lot of blur going on. Something I'll point out, this is a little bit of a specialized capability. With ambient occlusion lighting, the way the math is done, I won't get into the details. There's a way you can adjust the maximum occlusion distance, and by tuning that distance and reducing it, you can do a couple of things. One is, you know, if you go inside of a virus capsid, let's say I go inside of the HIV capsid, one of the first problems you have is that that capsid is completely closed and it has very small pores. And so if you're trying to do a physically accurate lighting calculation, no light will get in there. It's like walking into a dark room, right? So that's the result you see on the far left. One of the features VMD has for dealing with this is a maximum occlusion distance. So you can tell VMD to limit this occlusion distance to a shorter test range. And that way, if there's nothing blocking light within a certain distance, we pretend like there's just nothing blocking the light at all. This is, first of all, most useful when you're in the interior of a closed capsid and you want to look at the inside surface of the capsid and you're not interested, and you don't want to have to chop the thing open or otherwise modify your structure to make the scene more viable. You can just change this number. So it's just a selector. And once you've set that value to a lower value, say half the If you chose a maximum occlusion distance about half the radius of the capsid, that's sort of what you're seeing in the second leftmost panel here. And an interesting fact is if you then go further and further and further and reduce that occlusion distance down to a very short number, it has the impact of highlighting features at a certain spatial resolution in the structure. So if you see on the far right here, we see just these narrow crevices are shaded, or where we see the shadows accentuating those crevices. So that number, this occlusion distance can be used as a tuning knob to do things like show pockets or pores of a particular size more clearly than those of other sizes. So that's worth being aware of. Another advanced rendering feature that VMD has that, as far as I know, others don't, is what we call transparent surface peeling. When you go to make as I was saying, it's a very common operation to want to show the atomic structure, but show a transparent boundary surface for context reasons. If you do that with even some of the nice surface rendering and transparency materials that VMD offers, if you have a very stringy or overlapping structure, you can get a scene that looks like the image on the left, right? That's very difficult to see. And so if our goal is communication, and if the goal of the outer surface is primarily that of providing context, then really we don't need to see all of that detail. The detail of the surface is actually harmful to the seeing the atomic structure inside, seeing those ribbon representations. So what we have is a way of telling VMD not to render all of the transparent surfaces. What we can do then is tell it to render only the first one it sees and to hide every one of the transparent surfaces after that, or to draw the first so many. In fact, it's just a number. So we can tell it, show me the first one, the first two, the first three, the first n. And that gives us an image like the one on the right. So this is something that's built into the tachyon renderers that are in VMD itself. You can also use with the ray tracing engines, you can have reflections. So you can make a chrome type material, and then you can, make a very, very aesthetically pleasing visualizations like these. These are some zoom ins on a large finite element mesh surrounding a protein structure. And let's see, I already got that. Another thing that's interesting is as I pointed out before, with the ambient occlusion lighting makes it easy to identify things like the pockets, pores, and cavities. In this HIV capsid, you can see it's composed of a large number of hexamers. Every one of those hexamers has a little pore in the center. If you had to adjust the position of a light manually to see that, to see that shadow, you'd have to have it in just the right place. And as you see, over that surface, this is a sort of a spheroid surface. These HIV capsids are a closed surface, so they have the surface is composed of hexamers, except to make a closed hexagonal tiling, you need 5 pentamers. So down here you see there's 12 pentamers. Misspoke. 12 pentamers. There's a pentamer down here in green. We want to be able to see all these features. You can see how the surface is curved as it goes around. If we had to adjust the position of things like lights manually, this would be a really painful task in any software. And so that's one of the benefits of using things like ambient occlusion lighting on your behalf. As a scientist, you can just turn it on, rotate the structure, and in whatever position it takes, you'll be able to see those features automatically. One of the opportunities for things like head-mounted displays, VR headsets, because they permit you to, intuitively navigate the camera just by looking around, just by literally walking around in the scene or similar. Like here's a case where one of those small pores in a hexamer, there are ions that transport through there. And we want to be able to see a view like this. Doing that with the mouse can be a real pain. This is a case where you may want to use VR headsets to do this. You could also do it by creating a movie with omnidirectional projections and putting the camera down in the pour. Another way of doing it that's better than using the mouse, those of you who use Linux, there is a device called a Space Navigator. It's a 3D mouse. I don't know if you guys can see my camera still, but I'll hold one up so you can see it. So this is a fancy one. These are basically a 6 degree of freedom mouse. And using that kind of input device, you can rotate the scene and translate it in X, Y, and Z simultaneously. And so it makes it very easy, or considerably easier, if you don't have a head-mounted display or VR headset. It makes it very easy to fly around and put the camera down into a place like this with that level of detail. And it's very intuitive. So that's VMD supports all those kinds of 3D input devices. And so I just make you aware, there's Space Mouse and Space Navigator are two of the ones that are very popular. So you can use all these things to make nice journal figures and covers. And I would say those are, you know, some of the reasons we got into all the ray tracing. One of the things that's happened in the past 10 years is that ray tracing went from being a completely software-based technique to being accelerated by hardware. For very large scenes like these light harvesting complexes where we have tens of millions of atoms, or if we have, like in the scene on the right, maybe a large number of those, over a few hardware generations, you know, NVIDIA brought accelerated ray tracing into the GPUs. And so now even video games are beginning to use ray tracing to get higher fidelity rendering. But for molecular visualization, it is also tremendously useful. And if you add this then on top of all the stuff that I described earlier, this allows us to make visualizations of scenes that would have billions of atoms, even interactively, on state-of-the-art hardware. So this is a slide I made several years ago. So it isn't state-of-the-art hardware, but just to give you an example, there we have a Volta generation Quadro compared to one of the earliest hardware accelerated ray tracing GPUs, and there's a factor of 8 performance. And this is the thing that is going to allow us to change VMD's main viewport renderer from using OpenGL to being able to do interactive ray tracing all the time. So that hardware acceleration means that it's fast over the entire range of system sizes. And then we can do things like several years ago, we did a what we call a full dome movie. This was a movie called Birth of Planet Earth. So this combined a bunch of the things that I described, where we used a panoramic camera. So if you look on the left image here, there you see this, what looks like kind of a circular image in a black frame. That's actually what's called the Dome Master fisheye projection. And that's a hemispherical projection that is done when it's rendered in VMD. That is exactly what a planetarium display uses. So if you see the middle image, then this is that same kind of scene, then projected in a large format planetarium with a big audience. And for the audience who's sitting in the room, it is an undistorted image. You know, this is the photo of the room was done with a fisheye lens camera, so that's why it looks a little warped, but that's why the audience looks curved. And then, so VMD is able to use all those things to make movies like those. So not only can you make movies for YouTube and VR, but you can also make movies for planetariums. And I would love to see more biomolecular simulation and structural biology content in planetarium shows. I think it'd be awesome. And if you're curious, you can watch Birth of Planet Earth is on Amazon Prime. You can get it and watch it online. This is also how all the visualizations that were done for the recent COVID work with Romy Amaro and many of our other colleagues, Arvind Ramanathan, and as you see, a long author list. All of those exploited these ray tracing techniques to allow visualization of the entire virion, the aerosolized virion, the spike proteins, and many other components. These are all things that you can do on your own machines. As long as you have enough memory on the machine to load the simulation that you want to work with, all of this is doable. And this was done several years ago, so it's easier now than it was then. One of the areas where we're putting in effort going forward, over the time period that I was leading development of VMD, there was no way during that time period for VMD to get access to advanced rendering techniques except for us to write it ourselves. Now it's a little different, or it's becoming different. Going forward, there is a standards effort called Inari, which will create rendering techniques like what I have just shown you in VMD that run on a diversity of different vendors' hardware. So that makes it portable across different vendors' GPUs and software platforms. And this will make it possible for VMD to use more of those kinds of advanced rendering techniques in an automated way. And that allows you to use renderers, not just the ones that I wrote that are built into VMD, but also the renderers written by Intel, by NVIDIA, by AMD, and various open source renderers. And in fact, there's an Inari backend that connects to Blender. And these all have their own strengths and weaknesses and different features. But just to give you a taste, here's that same satellite tobacco mosaic virus shown in VMD. On the left is the renderer that I wrote that's built into VMD. The middle is the Intel Osprey path tracer. And on the right is an optics path tracer that one of my colleagues at NVIDIA had written. And this is a snapshot of the way things were about a year and a half ago. So actually it's a lot further along since then. And one of the cool things we have now is a way of connecting VMD using Inari not only to those built-in rendering engines, but also to outboard rendering engines. So for example, Blender and NVIDIA's Omniverse are two very large, sophisticated rendering packages. There are things that they can do that go beyond what the ray tracers in VMD, for example, will do by themselves. And some of those things relate to if you want to bring a molecular scene in conjunction with something else, whether it's a CAD model of a nano device. Let's say you're making a DNA sequencing nano device, and you have a big silicon pore and you want to show where the transistors are and things like that. Well, those are things that, probably are outside the scope of what VMD is really good at. We could show the slab of silicon as a large block of atoms and so on. But if you wanted to show a more CAD-like rendering of that nano device geometry, that's probably best done in another tool rather than VMD. So this is interesting because it allows us to combine the best parts of what VMD does with other tools. So these can be tools where you sketch things in 3D. It might also be good for creating illustrations. VMD's strength is to visualize the atomic structure and the understanding and analytical tools that it provides, but it's not really meant as a sketching tool for like you would use in a more artistic program. And that's where there's an opportunity to connect to some of these other things. So this allows us to take VMD's geometry and directly use the rendering and features of other tools like Blender and Omniverse. Since I work at NVIDIA, NVIDIA's Omniverse goes in a little broader direction. One of the things that's interesting about Omniverse is there's a way to have a live link between a tool like VMD and Omniverse. So if you make a change in VMD, it is immediately reflected in Omniverse. Omniverse then also has connectivity to display, real-time display in VR headsets. So for example, everything from the Meta Quest VR headsets, the Varjo headsets, Apple's Vision Pro, I think, is now supported. Another thing that Omniverse can do is you can run a visualization in Omniverse and send it or stream it remotely to an end user. VMD has some functionality for that built in too, but it only works on certain hardware. So these are things to be aware of. The opportunity for collaboration is interesting, and this backend that I'm talking about uses Pixar's USD. So that is a file format that connects to a bunch of different visual effects tools. So while what I'm talking about here are primarily Blender and Omniverse, there are a whole bunch of other tools that now work with USD files. So for example, Houdini and others. So this is a way, if you want to do things that are sort of outside the scope of purely molecular visualization, or you want to be able to maybe do fancy camera choreography or other things that are probably not well suited to a scientific visualization program, this is a way to accomplish that using the Inari features that we're adding to VMD. So a few weeks ago, I did a little talk like this for a cell simulation workshop, and I thought it'd be fun to show this group some of those things, just because although these happen to be coarse grain cell simulations, there's some common ground with, all atom simulations. So you can begin, just to give you an idea of how you can begin making images and figures, even if you've never seen the data. One of the problems that people doing cell simulations have is whereas the PDB has defined standard atom name and type and nomenclature schemes for the residues and all the other structure components, when you start doing things with cell simulations, it's a little bit more the Wild West. So the naming of the particles and all that is kind of up for grabs. And so it's interesting. It's a little different process, but it lets me, I thought it'd be fun to show you this because it's a little mental exercise about how you can use what VMD's tools are, even if you have never seen the data before. So I had one of our colleagues gave me a copy of one of the simulation trajectories, and he gave it to me the night before my talk. So I had about 30 minutes to, to dig up his files, load it, and do something with it. So if we just load up his structure and display it as points, we can already see there's a, a nice spherical cell model here, and there's some constituent particles in the interior, but we can't really make any detail out. If we just do a few simple selections to remove solvent, which granted, I had to figure out what the names of the particles were for the solvent. Already we go from, sort of a fuzzy mess to now I can actually see, DNA and some of the constituent structure on the inside. If I change the shading a little bit, add a little more color, make some more selections, I go from that to this. I can start to see a little more depth there now. If I then stop drawing it as points and actually draw it as like van der Waals spheres and using ambient occlusion lighting, I've done like 3 things. So this took less than 2 minutes to make this, knowing, and I didn't even know the names of the particles, so knowing nothing, you can make a figure like this in a very short time. Then you can start doing things, chop open or make different atom selections. VMD allows you to make geometric atom selections, so you can use equations to select things that are interesting to see based on their spatial coordinates. So that's how you do a cutaway like this. And then you can orient the camera and so on. So I thought I'd just show you guys these things are kind of fun to look at. Oh, and then the last one, I just tilted a little different angle and gave it some depth of field. So you can see the things in the foreground are in the crisp plane of focus, and the things in the background are blurred away. So, and I think my total time spent, it took me longer to download his files because it's 100 million particle simulation. It took me longer to download his files than it did to, turn it into a viable picture. And so I just did that as an exercise to show others what you could do, even if you don't know these details up front. This and the nomenclature stuff, this is often one of the things that makes it hard with different people's data. If a friend or a colleague sends you their simulation and you want to visualize it or study it yourself, often it is the way they've chosen to name things. It was meaningful to them. It may or may not be meaningful to you. Those things end up being more of your challenge than the use of the software, at least in my mind. But and at this point, I guess I'm happy to take your questions.
This last part was awesome, John. It's pretty cool to see this new representation pretty fast. Any questions for John now?
And you may need to repeat, Raphael, because you are very soft. I can just barely hear you.
Is it better now?
Yeah, it's better.
Okay, I'm gonna stay closer to the microphone.
Very good, sir.
How many particles do we have in this model?
So how many particles on this one?
I think this one's 100 million, but I'm not showing that many. I'm probably only showing, I don't know, let's say 60 to 80 million or something like this. I don't know exactly.
Almost nothing, right?
Yeah.
So, by the way, like on that question, like what is the limit of VMD? I remember seeing you showing things with billions of particles before. So what is the
largest one I've personally loaded as a non-replicated structure is on the order of 1 billion. And, that was a trajectory, and I needed a machine that had almost a terabyte of RAM for that trajectory. We did it. Actually, the machines are still at the TCB group at Illinois. Imad's got, I think, 3 large memory machines. And there are some VMD, by the way, if you get into this regime where you're doing stuff with cells, there are some ways to compile VMD to use less memory even than the normal version that does. So, when we're doing all atom simulations, there are a bunch of heuristics that VMD uses to provide very high performance. And those, heuristics, we spend some memory to make things faster. But when you're going for 1 billion atoms, sometimes the memory capacity might be, especially if you're doing a trajectory, maybe we care more about the memory than the other things. So anyway, there's some things you can do to reduce how much memory VMD uses by doing a simple recompile. But aside from that, 1 billion atoms is well within the stock version. I did, over the past year, I had some patches that I had been testing for a long time to, like the stuff I showed earlier in the talk where I made the cell model load 6 times faster. Some of the stuff I did for atom selections, I wanted to make sure, exercise it for a long time before I put that stuff in the standard version. But for example, all those things are in there now. Every bug fix, everything that ever broke up to 1 billion atoms is in the current version of the code now. So it's pretty awesome. The hard limit really right now would be somewhere around 2 billion atoms, and if they're not a duplicated structure. Now, if we go back to, I think that was the last one. Let me go back earlier. I'll show you this scene. Yeah, this one. So this scene here, I should dig up the other one. We have a version of this scene that has hundreds, or maybe it's thousands, I've forgotten. It's either hundreds or thousands of chromatophores, each of which is 100 million atoms. That is done using a technique called instancing. This is another superpower of ray tracing. There's a way to, with a ray tracer, you can make copies of something, and the rendering cost of drawing another one is negligible. Whereas that's not true for OpenGL. So if you're doing something like this, where you're looking at a vesicle, within a cell, and you want a large number of them, this is done basically for free. These things we can do huge numbers of copies of, I don't know how many billions of atoms, but the individual particle, the individual vesicle rather, that part would have to be less than 1 billion atoms, but then you could have as many of those. I don't know what the limit is. We've never come close, I can tell you that much.
Thank you. Any other comment?
On the Auburn machine and GPU and
Oh yeah. So the question here is like, what kind of what is the average machine you recommend, type of memory and like type of GPU? I know you're gonna say NVIDIA, that's the answer, but like, but like what is like for the average user that runs like 200,000 atoms to 1 million atoms, something like that? What do you recommend?
Yeah. So, well, the nice thing is, I'll give you a couple of items of feedback. The nice thing is, if you're doing something like this, where you're looking at a large number of fact. So one thing is that GPUs, the reason that ray tracing wasn't used 30 years ago on GPUs was because GPUs from 30 years ago had, maybe 8 megabytes of memory, right? Whereas GPUs of today, a top-end gaming GPU has 24 gigabytes of memory. And ray tracing, one issue about ray tracing is it needs memory. That's one major difference between ray tracing and rasterization. And that was why, by the way, even though we've had ray tracing in VMD for decades and we've had it on the GPU for more than 10 years, right? Even though we had it on the GPU for more than 10 years, 10 years ago, we couldn't have drawn a scene like this on a GPU because we didn't have enough memory, but now we do. So even a gaming GPU has enough memory for this. So if you were to get like an NVIDIA RTX 4090, for example, those are wicked fast GPUs and they have 24 gigabytes of memory, and that is more than enough for any normal scenario, right? Now, NVIDIA makes GPUs with more memory. They're like the GPUs that I use most of the time are an RTX 6000, which is a Pro GPU that has 48 gigabytes of memory. It's actually a slower GPU than the gaming GPU, mainly because mine is something like 4 years old. I don't remember how many years old it is, but it has a lot of memory. And because I spend a lot of my time developing tools like VMD, I'm more concerned with crashing the programs and finding their limits, right? So I want to feed them with my test cases for VMD these days are huge things, right? So I tend to do it for that reason. But a person who's only simulating something in 100,000 to 1,000,000 atom range, I would say any of the gaming GPUs. I don't know not only do I work for NVIDIA, but I also just never cared that much about the other brands of GPUs. So I don't even know. I don't even know what their comparable models are. But for those of you who are into these things, in NVIDIA's gaming GPUs, for if you're buying one for yourself, a 4090 or a 4080 are fine. These are GPUs that have 12 and 24 gigabytes of memory. They would be great, and that'll work for several years. Just a second, I get a drink here.
Okay. Thank you, John. Any other question? Yeah, we have another question here.
Yeah, might have mentioned it, but is the ray tracing only done at render, or is it like done in the viewer as you're kind of moving things around? And
So, John, the question is, can you use the ray tracing only rendering, or you can do a live, like OpenGL window, like rendering with ray tracing at the same time?
Well, I guess there's three answers. There is batch mode ray tracing where you can, and that's how the software-based ray tracing in VMD has always worked. Was the software-based ray tracing was based on my Tachyon ray tracer that was written for CPUs originally, and that one, the CPU version of Tachyon is only used for batch mode ray tracing or offline rendering, right? Then there is a GPU version of Tachyon. That is what's built into VMD, and that is interactive, but for a static scene. So that means you can rotate the scene around, change the lights, turn various rendering features on and off, all that kind of stuff. More like what you do like in Blender, right? Or something like this. And that is, but it is interactive in that you're able to, that may display at 30 frames a second, right? That's all fine. Like a scene like this, for example. And then the last one, which is the thing that's new, and that's what, when we were talking about VMD 2.0, the last thing is changing the entire VMD viewport renderer, the main window, to use ray tracing. That is a new feature. So there is a way to, if you want to compile VMD from source, this can be turned on. And but we have this prototype in there now, and that basically does everything using ray tracing all the time, even when you're interacting with the main user interface. And so that the goal is then that will become part of VMD2 by default. And we will have, because of the work that I did before I joined NVIDIA, and of course the work that I continue to do, NVIDIA stuff will be awesome, needless to say. But to support the others, this Inari platform that I described earlier, the cross-platform rendering API, that will be used to get VMD to connect to the other vendor stuff like Intel and AMD also.
Thank you, John. Any other questions?